Welcome to the podcast summary of Meet Core AI from WWDC 2026. Today's catch-up is really about what happens when AI moves off the cloud and onto the device in your hand. The big theme is cost, speed, and privacy all getting reshuffled at once, with Apple's Core AI approach making local inference practical, while developers get better tools for startup time, debugging, and performance tuning. And underneath the nice demo version of that story, there's a lot of very real engineering around transformer caches, compilation delays, memory safety, and custom GPU kernels. One of the clearest takeaways here is that if the model runs entirely on an Apple device, the app can skip the whole back-end inference bill. No server sitting there eating costs, no per-token billing quietly stacking up in the background, and no need to scale infrastructure every time usage spikes. That's a huge deal for developers because AI features stop looking like an open tab at a very expensive restaurant. It also changes the privacy story in a pretty straightforward way. If the inference stays local, user data doesn't have to leave the device, which fits neatly with Apple's broader push around on-device intelligence. For users, that can mean a feature feels more personal without also feeling like it's phoning home every few seconds. Of course, running locally only feels good if it's actually responsive, and transformers are not exactly famous for being magically latency-free. A key part of making them usable is key-value caching, where the model keeps the right internal state from previous steps instead of recomputing everything from scratch each time. That sounds tidy in theory, but getting it working in practice took some careful plumbing. The caches had to be registered as buffers in the PyTorch module, then converted into Core AI states, and then passed back in during inference as mutable ND array views at every step. So the payoff is lower latency, but the road to that payoff is very much real systems work, not just flipping a settings toggle and hoping for the best. Another important piece here is model specialization, which is basically the work needed to tailor a model for a specific device. That can take noticeable time, especially with larger models, and it's exactly the kind of delay people feel immediately. If someone taps a feature and then waits while a model gets prepared, that's not a subtle UX issue. That's the app feeling broken, or at least a little awkward. So the advice is pretty clear. Don't put that work inside an interactive flow if you can avoid it. Core AI exposes a model cache programmatically, which gives developers some practical options. They can preload or pre-specialize models ahead of time, tell users when a wait is coming instead of surprising them, and remove old cached entries when storage starts getting tight. That's the kind of detail that sounds unglamorous until you remember it's often the difference between a feature people trust and one they abandon after one weird pause. A lot of that specialization latency comes from compilation, and that's where ahead-of-time compilation starts to matter. Developers can compile models on a development machine first and produce device-agnostic artifacts, which takes a big chunk of the heavy lifting out of the moment when the app is actually running. There's still a lighter device-specific specialization step afterward, so it's not pure magic, but it's much faster than doing everything from scratch on the user's device. And that improvement is meaningful because startup time is one of those things people notice instantly, even if they never use the phrase startup time in their lives. They just know whether something felt ready or whether it felt like it needed a coffee before getting started. On the developer side, the Swift API story is pretty interesting too. Core AI's framework uses modern Swift features, including non-escapable types, to guarantee memory safety without giving up performance. That matters because low-level model work is exactly where memory mistakes can turn into painful bugs, weird behavior, or plain old crashes. What's nice here is the API is designed progressively. You can get a basic inference pipeline running without a giant ceremony. But if you need tighter control for performance-sensitive work, the deeper layers are still there. That kind of design tends to age well, because it helps beginners get moving while still leaving room for the people who are going to obsess over every millisecond lovingly for weeks. There's also room for developers who want to go beyond automatic conversion and really tune how parts of a model run. With Metal 4, Core AI supports authoring custom GPU kernels, which opens the door to fine-grained control over specific operations. That's especially useful for niche model components that generic kernels may not handle efficiently. So instead of accepting whatever default performance falls out of the pipeline, developers can optimize those tricky pieces directly and squeeze more out of Apple Silicon. It's a reminder that the platform story here isn't only convenience, it's also about giving experts enough levers to actually push performance further. And then there's debugging, which is where AI work can get humbling fast. Core AI Debugger helps by showing intermediate tensor values and connecting them back to the original Python source. That makes numerical correctness, checks after conversion, much less of a guessing game. If something changed unexpectedly, you're not stuck staring into the void wondering which layer betrayed you. Alongside that, the Core AI Instruments gauge lets developers watch live activity and catch performance bottlenecks early before going all the way into deeper profiling. That's useful, because sometimes the fastest fix comes from simply seeing where the system is obviously unhappy before you start doing heroic optimization work. Put together, this paints a pretty coherent picture of on-device AI getting more practical and more mature. The headline benefits are easy to like: lower operating costs, better privacy, and faster feeling experiences. But the real reason it feels credible is that the supporting pieces are there too. Cache handling for transformers, ways to reduce specialization delays, a safe but flexible Swift API, custom kernel paths for experts, and better tools for debugging both correctness and performance. That's what turns on-device AI from a nice talking point into something developers can actually ship with fewer crossed fingers. That's the roundup for today. A lot of this is deeply technical under the hood, but the user-facing outcome is pretty simple. AI that feels faster, costs less to run, and keeps more of your data where it already lives. And honestly, anytime a system gets cheaper, more private, and less dependent on a server bill, that's a rare 3-for-1. This episode was generated by Podkey. Create your own at podkey.fm.